Oh, hi everyone. Wanted to see if you could please take a seat and get settled. Thank you. We're right at 12:15. Well, greetings, and I'm Rebecca West, and I'm the curator of the Plains Indie Museum. And you may be wondering what I'm doing here, but I've been filling in, working as an interim manager to work with these wonderful Draper Natural History Museum folks. And it's my pleasure to do a few announcements this morning before we get to our speaker. First, I want to thank our sponsors, the Sage Creek Ranch and also the Nancy-Caroll Draper Foundation, for their continued support of both the Draper Museum lunchtime expedition programs, but also the Draper After Dark programs. And I also wanted to reach out to a couple of my colleagues that are here. Gretchen Henrich, she's the Director of Education. She's been helping with the logistics for this program. And also Corey Anko, he's here, the Assistant Curator of the Draper. He's in the back. Corey, thank you very much for filming these presentations. So if you're wondering, and if you've missed a few of these or you have friends who'd like to see them, Corey is kindly filming these, and they will be all available, and many are already, on our website, centerofthewest.org. Before we begin, if you could all grab those cell phones, make sure they're on silent, please, so we don't have any random ringing during the presentation. And then finally, I have just a couple of upcoming presentations. Next week on July 18th at 5:15, we have another Draper After Dark presentation. So if you'd like to join us for that, we have Anthony Caragiulo, and he is speaking on Back to the Future, leveraging museum collections. And if that's not enough, you can come back on August 1st for another lunchtime expedition lecture. That's at 12:15. And that will be Mike Kochert. And so catch all of them if you can. But for the main presentation today, I am so pleased to introduce our speaker. He is Dr. Robert B. Smith, and he is a distinguished research professor and emeritus professor of geology and geophysics at the University of Utah, and he's been a faculty member there for 53 years. Impressive. And now he's noted also that he is on year 63 of his research on Yellowstone. He has received several medals, and I think he's being very modest about this, but awards also for his research from organizations such as the American Geophysical Union, the Geological Society of America, the British Antarctic Survey for service in Antarctica, the Antarctic Medal from the U.S. State, the National Park Service, Yellowstone National Park, and the Swiss Federal Institute of Technology. He's published more than 200 scientific papers, over 300 abstracts and reports, and he's also co-authored a book, and this is the most popular geology book in the Yellowstone-Teton area. It's titled Windows into the Earth, the Geologic Story of Yellowstone and Grand Teton National Parks. During this distinguished career, Bob served as the U.S. Exchange Scientist to the British Antarctic Survey in 1962 and 1963 on expedition to the unexplored Antarctic continent. And for this amazing expedition, he received the British Antarctic Survey Gold Award and the U.S. Antarctic Medal from the U.S. State Department in 1965. Very impressive, Bob. And also, finally, if that's not enough, he's the president of the seismology section and officer in the American Geophysical Union, and a board member of the Seismology Society of America. I could go on, but we want to let Bob have a chance to speak as well. So we are honored to have Dr. Smith join us today to discuss a fascinating and a hot topic, literally, anatomy of Old Faithful and Upper Geyser Basin and its ties to the Yellowstone Magma Reservoir. Please welcome Dr. Robert Smith.
Thank you very much for the introduction, and there's my book, and I'm willing to sign any if you wish. If you have them, I'm doing a second edition, so the libraries cannot get it anymore because Oxford University Press says, Smith, get it done. second edition. There's the first one, and I'll sign any of you brought if you wish. Welcome and thanks for everybody who's here, especially in thanking the staff who invited me for the presentation, and to my long-term host, Bob Richard, we've worked together for many decades, and who I'm staying with, and we want to recognize Bob and his contributions. Well, I'm telling you that these guys know more about Yellowstone than many of us do. And I want to tell you right now, Yellowstone ain't about to blow. In spite of, these are all recent press releases. And we deal with these press releases about once or twice a week, that it's about to blow, and we give results. Don't believe any of this unless you call me up and verify it. But Yellowstone is not in any situation where it's going to create any kind of eruption. Well, first of all, my title, as you can see, Old Faithful Anatomy, which I'll talk more at the end of my talk. Then I'll talk about the deep structure of Yellowstone, and my overall outline is I'll give you a general geologic setting and then talk about earthquakes and volcanoes. And then I'll talk about the dynamics of Old Faithful. And of course, I have to say something about California earthquakes, right? A lot of you here may be from California, and it's shaking right along with a magnitude 7.1 just last week. I worked very long and hard in Yellowstone. As I said, this is what I'm showing you is my career-long research of beginning in 1956 in Yellowstone when I was a GS0. And I was able to study in '59 the Hebgen Lake earthquake as an undergraduate student, and I'm now into my 63rd year in Yellowstone. My research has been supported by these main research groups. This is my group right here, the Seismology and Active Tectonics group at the University of Utah Seismic Stations, which I originated. Of course, the Park Service, National Science Foundation, EarthScope is a group that was funded by NSF that I was the chair, Yellowstone Volcano Observatory and Teton Science School, which I also helped form, and a couple of foundations. So my combination to you is 40, 50, 60, 70, 100. I have to keep that on my combination on my lock. 44 years ago, I helped found Teton Science School, so that's 40. 53 years now, actually, at the University of Utah, where I'm a distinguished professor. 63 years in Yellowstone, beginning just out of high school. And I've supervised 70 graduate students, which is a record, at least for our university. And if you add in all the honors students, postdocs, the number is 100. So I've had a lot of education and teaching and research with a lot of different people. And I acknowledge their support, especially with all the research that we do. I want to point out that Arnold Haig, anybody remember him? How about Ferdinand Hayden? They were part of the Hayden survey in 1873. Well, these two guys I met up with at Muir Plateau, and on the left is John Lonsberry, who is the district ranger. On the right is Bob Richard, who was with us. As I said, we were studying the Muir Plateau and the Big Fault, and we were there not in 1871, but the Ferdinand Hayden survey was. So I dedicate my talk to Bob Richard. I appreciate his support for so many years. Here I am at the Fern Lake cabin with my three great Yellowstone friends of decades. On the left is Bob Richard, on my left, on your right, and then the middle is Jerry Mernon. You may have heard of the long-term district ranger on the right, John Lonsberry. Guess what we're trying to do? If you ever know Jerry Mernon, we were trying to tie his double-double diamond hitch, and none of us could do it. So he reached over and did it and said, let's get going, guys, you'll never learn. Well, Yellowstone is a hot spot in plate tectonics term, and you can see it's, of course, up here in the northwest corner of Wyoming. And most hotspots are in oceanic settings. But in plate tectonics, there's 4 major elements. And the western US has all of them. We have the transform fault here on the San Andreas, for you Californians. We have subduction zones in the Pacific Northwest up here, where the Juan de Fuca plate is being pushed eastward beneath North America, Washington and Oregon. And we have the basin and range, extending from Salt Lake City, if you wish, to Reno. And the basin range is an area of active extension, meaning the crust is pulling apart at 1 or 2 inches a year between Salt Lake City and Reno. When you pull something apart, you break it into faults. And that's why we have mountain blocks and faults every 25 kilometers. And of course, Yellowstone. And that's 1,500 kilometers, from the plate boundary. So it shouldn't be there. Well, I'll explain why it probably is. If people know me, I like to integrate different kinds of information. So on this slide, which is a little bit busy, I'll start over here. Yellowstone is at the top. But what makes up or what contributes to Yellowstone? Those hydrothermal features, volcanic features. We have a lot of earthquakes. We have magma that releases heat. We have ground deformation. And we have a mantle plume deep in the earth. Now, these are all double arrows. And they relate to one another. Starting clear deep in the earth, magma comes up. And here's a figure showing the latest of the source of Yellowstone in red. So this is a colored picture of, if you wish, temperature. It's actually seismic velocity, but the Yellowstone starts down here at a depth at least 1,000 miles, and it comes up not vertically, because it gets kinked in the mantle flow, and then it comes vertically beneath Yellowstone. When it hits Yellowstone, it created 2 volcanic systems. One at a depth of, you can see, I'm sorry, these are miles, 15 miles to 30 miles is the lowest partial melt. Yellowstone is underlaid by magma, but not 100%. It's like having a sponge with maybe 10 to 15% melt in the pore spaces. It's not a magma chamber that you see in all the books, or none of them are for that matter in geology. And then when it comes to the surface, the magma rises, it fills the upper melt system, the upper crust, which is only a depth, if you can see, about 5 kilometers, so only a few miles. It underlies, and that's where we get the source of heat from Yellowstone. And when this chamber fills, it causes the ground to deform. So here's a contour map of uplift, just like on a topographic contour map. And this is topography related to the uplift between 2003 and 2008. So this is a very dynamic system, and we make these maps up from satellite interferometry. So I take the approach, I study all these topics, and because you have to understand one related to another, and you'll see my approach as I go along. Well, why do we need to know geology? The three-dimensional geology is such that we have the Yellowstone caldera right here. Cody, by the way, is right over here on the east side of these purple rocks, the Absarica Range. And we have heat coming up, and I'll show you the magma source. And it creates the volcanism of Yellowstone. And this is the map I tried to make back in '80 of the caldera outline, the shallow crust. This solid granite batholith, that means it's solid granite, but it's hot, because it's heated from below. And even in 1980, we didn't know where it came from. I'm going to show you where it came from. First of all, you guys love to go to Yellowstone, right? It's always uphill. You can't get to Yellowstone from Jackson, Cody, Bozeman, West Yellowstone without driving uphill, because you're coming up on top of a broad plateau. We call this the Yellowstone Plateau. And this is the Teton Range, which, by the way, used to extend all the way up through to the Gallatin Range. But the mountains are gone. And the Mount Sheridan is cut off. This range extended across Yellowstone. Chicken Ridge, this range extended across. They were all blown away in Yellowstone volcanism. So the first big eruption, we know the south boundary, that's Caldera #1 right here. So we know its boundary reasonably well. Island Park is a young caldera. It's the second oldest. But the Yellowstone caldera is #3, and it's only 640,000 years ago. So there are giant eruptions, super eruptions that accompany the creation of a caldera, which I'll show you. And then there's 2 resurgent domes, Mallard Lake next to Old Faithful, Sour Creek just north of Fishing Bridge. These are like pistons that stayed high while the ground subsided around the caldera. Now the Yellowstone is, 300, the whole swell extends from Cody clear over the Madison Valley, almost from Bozeman clear south of Jackson Hole. So it's 300 miles wide. It's not just Yellowstone National Park. That's just a little pimple on the top of it. Well, this is Steamboat Geyser erupting in 1984, and I happened to be flying along. I was out of fuel and I was out of film, but I went straight to what I thought was a forest fire, and this was my last picture. And there it is, the only aerial picture of the world's largest geyser, Steamboat. And Steamboat erupted July 6th. The water reservoir was probably 300 to 400 degrees centigrade, and the steam, hot water, and mist rise to 400 feet. And I flew right through that, turning around. And it's the only eruption that has ever been taken aerially. Now, the chances of me taking that picture are 1 in 150 million. The same as winning the California Powerball lottery. The overall picture of this whole system is called the Yellowstone Snake River Plain System, and it begins down here in southwestern Idaho, southeastern Oregon. And I've plotted here, this is the background topography. Earthquakes are plotted in red, and these yellow centers in millions of years are centers that contain many, many super eruptions. Dozens sometimes. So we go 16 million, 14, 12, 11, 10, 7, 6, 4, 1, Yellowstone. So this progression of young caldera systems is the result of the North American plate moving across this hotspot. So that's the track, and there's another track over here to the northwest called the Newberry Volcanic System. 10 million, 8 million, 4 million in the Newberry caldera. It's not nearly as strong as the Yellowstone systems. And then we have these basalt, these are dikes of basalts that came up 17 million years while the basin range was splitting apart. So Yellowstone is part of an active, dynamic geologic system. Well, how do calderas form? They form when you bring magma, and in this picture it's kind of diagramized, it's 100% melt, it's not quite 100%. You bring magma up on a vertical conduit, it spreads out because the upper part of the Earth's crust is brittle, cold, and weak, and it's strong, and it doesn't want to break. But eventually, if you get enough melt in here, and here's the actual melt and the mixed hydrothermal melt, gets big enough, it finally raises the surface, you get enough pressure, and bang, we get an eruption. That is the origin of a caldera, because when you remove the roof support, the surface just collapses back into a hole. And Yellowstone has 3 calderas within it. And I'll show you the outlines of these systems as we go. Well-known volcanic eruptions, you probably all remember some of the more seasoned folks. 1980, Mount St. Helens. And Mount St. Helens had this giant explosion of gas, blew out the flank of that mountain, 0.3 of a cubic kilometer, so roughly the volume of this area right here at the Buffalo Center, high and wide, and it killed 60 people. In 1991, there was an eruption in Mount Pinatubo. Mount Pinatubo used to be right here. It blew away, 1991, 7 cubic miles. That's like the size of all of Cody, and with a kilometer or two high. And it killed 700 people. Well, typical Yellowstone post-Caldera eruptions are 5 to 10 times larger than Mount Pinatubo. So these are giant eruptions that are in our backyard. How do they form? Well, here's a little test. You take a tube filled with resin, you put a Bunsen burner on it and heat it. So here's a movie showing, there's the heat source is down here, and you boil the resin, and bubbles will exsolve, that is oxygen and CO2. You'll start to see bubbles coming up. See these bubbles rising? There's a big one here. There's a nice one right here. There's a nice one. They rise up through this body into the tube, then they explode violently. Now this is a real sample. I mean, the dimensions here are about 3 feet by 4 feet. So it rises up in this column and then it falls back down, and this would be the pyroclastic flows, the ashes and the dust that just flow out tens or hundreds of miles in the case of a big eruption. Okay, Yellowstone has had 3 major caldera. Here's the first one, 2.0 million, 2 years old. Here's Island Park, 1.3 million. And here is, quote, the Yellowstone caldera. And the Yellowstone caldera was 640,000 years ago. The last event time, of course, was 640. The average inter-event time is 710,000 years. Now, if I take the inter-event times here, 800, 600,000, and I average them, you know, that doesn't mean very much, because the average event time is 700,000 years. But who in their mathematical skills would take 2 numbers and calculate an average? None of you would. You would never use that kind of mathematics, just taking 2 numbers. So we really don't know from this information how close we are to the next eruption. Don't have a clue, but I'm going to show you how we monitor it and how we can measure it. When Yellowstone erupted, the ashes covered much of the western U.S. This is the oldest ash, Huckleberry Ridge Tuff, and the youngest one here. And you can see it covered all the way down to the Gulf of Mexico out in the Pacific. In terms of volume, these 3 cubes right here are Yellowstone volumes. 600 cubic miles, 240 cubic miles, 67. And these are pikers. There was an eruption in 1815, Southwest Pacific, 36 cubic miles. Mount Mazama is the center of Crater Lake National Park, 18 cubic miles. Krakatoa, that blew out Southwest Pacific, 4 cubic kilometers. Mount Pinatubo, 2.4. And St. Helens is a piker, 0.3. So Yellowstone truly have supersized eruptions, and when we map the surface, the youngest rocks are Lava Creek Tuff right here in green. They cover all of Yellowstone, the caldera, and they float all the way down into the middle of Jackson Hole, down to the southeast arm, the thoroughfare. Then the next oldest rocks are the rocks around Island Park, and the very oldest, Huckleberry Ridge Tuff in purple, also float all the way down into Jackson Hole, all the way up in toward the Paradise Valley and the Madison Valley. So these eruptions did cover a great deal of this part of the world. Now this was my idea, and it's in my book, about what actually happened. The super volume was 2,500 cubic kilometers. That fills the Grand Canyon twice. So if you visit the Grand Canyon next time, say, whoops, if I fill that once and then twice, that's an enormous amount of eruptive material. The eruptions tend to begin on a rim fracture zone. This is a circular oblong ellipsoid, if you wish. These are the ring fractures. These eruptions supersize, last weeks to months, maybe even to years. And gas and ash rise up to 80,000 feet. And if you were flying an airliner in those days, you would have a lot of problems. Most of the rock that actually is blown up into the air falls back into the caldera. So don't get the idea when you have an eruptive event that most of the magma falls out. It doesn't. It goes up and just goes back down. Maybe 10% is on the surface and on the edges. But the temperature increase is up to 9 degrees centigrade. So 10 to 12 degrees Fahrenheit, and that lasts for years because of all this material. So that gives rise to volcanic winters, and they can last for decades. Okay, it's a swell, I just told you that. I'm going to show you a few pictures. If you go to Madison Junction next time, here's Madison Junction right here. Here's the road looking to the south, Old Faithful. There's the rim of Caldera number 3. And the road turns right here at Madison Junction, goes up the Gibbon River, or left down to West Yellowstone. This is the edge of the last giant caldera. But the edge of number 1 cut off, this is the Mount Holmes area, and Mount Holmes was cut off in that first giant eruption 2 million years ago. So these are the physical evidence of these things. If you go next time to the Firehole River, how many here like to go there and swim? If you stop in the parking lot to swim next time, that's great. Look behind you. These are the rocks in the parking lot. This is rhyolite melt. You can see this is like batter from a pancake as the molten rhyolites float out onto the surface. There are chunks of solid rhyolite, molten solid, they all consolidated and formed the topography at the parking lot. And right there when you stop, next time take a look. So it's always uphill to Yellowstone. Now I'm going to show you some new photography. This is LIDAR, light imaging reduction system. So we use light, well, so it's radio. And this methodology shows the topography with the vegetation stripped off. So it shows the bare earth topography. So here we are at Fishing Bridge, coming down the Yellowstone River, and the big Sour Creek Dome is right here. And look at the big, these are faults, these linear breaks, because as that dome came up, at the center of it collapsed. There's also faults that come along the Elephant Back fault zone, and it goes north to the, this is the Muir Plateau, by the way. Look at these faults, these little lines right here. These are faults that accompanied the collapse of the caldera. So they're very vivid in LIDAR imagery. And if you go down to Old Faithful, here's Old Faithful right here. It doesn't show anything really exciting. There's the Mallard Lake Dome. It is exciting. These are northwest trending faults, and the center of the dome collapsed. And there's a little lake right here that formed right in the middle of the dome. Old Faithful's here, and of course you just see the open topography, upper Geyser Basin, lower and middle Geyser Basin. So we use this kind of photography, LIDAR photography. It's expensive to fly, but we get very detailed data. Well, geology is what makes Yellowstone famous, and I have to tell you, up until the early 90s, it was not appreciated. But of course, these two main features, the lower falls of Yellowstone and Old Faithful. Well, Doane was a lieutenant in the Army. He rode through Yellowstone in 1870, and he said, as a country for sightseers, it is without parallel. As a field for research, it promises great results, geology, mineralogy, botany, zoology. It probably furnishes the greatest laboratory that nature furnishes on the globe. How right was he? He was right on. So, as I said, Yellowstone is a geologic park, but it wasn't really appreciated until the 90s, and I'll tell you why. Oh, by the way, this is all contained in my book, the Geologic Story of Yellowstone-Teton National Park, if you're interested. This is what really turned the world on to Yellowstone. BBC put out a production in 2004 called Supervolcano. How many here have seen it? Well, if you haven't seen it, you should. It's online. It's an amazing documentary. We help them, by the way. But they kind of overemphasize things like, here's the forest, here's the giant eruptions. But when they produced this document, they named it the Yellowstone Supervolcano. I kind of like to call it the Yellowstone Giant Volcano, but globally it's become the supervolcano. And so 2004 on, people recognized Yellowstone was a major geologic feature and park. Well, it's famous for hot springs and geysers. This is a map showing in red all of the hydrothermal systems. Hydrothermal systems means geysers, hot springs, fumaroles, mud pots. And you've all seen Old Faithful, the Upper Geyser Basin, Midway Geyser Basin. This is a corridor from Mammoth to Norris, and there's the Norris hydrothermal features. But here's the biggest one in the world, Hot Springs Basin. It's a 20-mile horseback ride or helicopter trip straight north of Old Faithful. But the majority of these lie within the Caldera boundary. And my idea of the model of a hydrothermal system is you have a source of heat. It heats a layer of saline water. Saline water boils, just like in your coffee pot. Saline means it's heavy salt rich. And it in turn heats the groundwater. You can see these little convection cells. The groundwater then boils, gas, hot water, steam evolve, and we get Old Faithful, hot springs and fumaroles. The question is, where does the heat come from? Well, I just want to make sure you know, next time you're out in the park, you have to visit Old Faithful. A good time is about the middle of February. It was 45 below zero when I took that one with Rick Hutchinson. Guardian Geyser down the road, Beehive Geyser further down the road, and Beehive erupts almost continuous, not quite continuously, but you can go there any day and see multiple eruptions. Here is some of the interesting features around the northeast side of Yellowstone. This is Hot Springs Basin. This is an area 2 miles long and 1 mile wide of hot steam sulfur coming out of the ground. And you can see the sulfur right here. It's being deposited through hot vents naturally. If you go down the trail a ways, you come to what we call totem forest. This is where Broad Creek turned right just before the Yellowstone Canyon. And you can see these vertical deposits. So mineral-wise comes up and then deposits on the side. So I called them the totem forest, and Rick Hutchinson and I named it that. And the Park Service came along and said, oh no, it's the Fairyland Basin. I said, oh no, it's totem forest. That's the name. Way before the Park Service did. Now, I have a colleague. Can you hear this? This is a experiment done by a late professor, Dr. Westphal from Caltech and JPL in California in the 80s, late 80s. He came to
You're
Yellowstone.
watching Old Faithful for
He's
the last few
going to put a
minutes
television
before
tube
interruption.
down into
We would
Old
like to
Faithful.
tell you a bit about this video.
Can you hear
A
it?
small group of scientists from the California Institute of Technology, Arizona State University, and Yellowstone National Park have been studying how Old Faithful works in detail. We are especially interested in geysers since they seem to work in very similar ways to volcanoes, like Mount St. Helens, yet we can safely work around Old Faithful. Some time ago, we made measurements of temperature and pressure.
We
at
were
several
using
depths
this
down
as
the
an
bed of Old
analog
Faithful.
of a volcanic eruption.
We collected
I was
data
with
starting from the time that it emptied out at the end of an eruption until it refilled and finally erupted again. From this work, we learned many details of how geysers work. But of course, we still have many questions. We'd like to know where the water comes from. Does it come from the sides or from the bottom or both? Why does it stop filling up at about 15 feet below the top? If you look down from the top, the vent is a slot about 4 or 5 feet long and about a foot wide. You can see down about 10 feet. But below that, we really don't have any idea what the vent looks like or what effect its shape may have on the way Old Faithful erupts. We wonder if the vent fills with water quietly or if it is boiling. Old Faithful also makes a series of big splashes before each eruption. You have been seeing these in the video. In fact, an especially large one usually triggers off the eruption. We don't really understand what that's all about. These and many other questions have led us to want to see what's down there. Just recently, it's been possible to get a very small television camera. As Old Faithful again throws a big bunch of water out, this time it probably is going to start the eruption. And indeed, that's the case. There is Old Faithful in full eruption.
At the orifice, the water is coming out at thousands of feet per second. And there's the orifice. If you stand right next to it, if you dare,
as I mentioned
you
before.
can't anymore.
It's covered with a material called sinter, which looks kind of like snow, but it's actually made out of silica, a very hard material that coats everything that gets splashed with the erupted water. Here is the little camera itself, out of the housing. It's about 2 inches long and about 3/4 of an inch in diameter, lens and hole. We now have the camera down into the vent of Old Faithful. It's about 6 feet down, and it's swinging on the end of its cable at the moment. And we will soon be on our way down to as deep as we can get safely. At this moment, we're still discussing exactly whether all of the hardware is working and if we have the camera properly hooked up electrically and the right microphones running and all those sorts of things. We want to make sure we've done everything right before we go in because we have no idea what's going to happen.
Now, this is first time it was ever done and last time it was ever done.
You can see the near wall of the vent in the bottom left corner of the picture.
It is not a round conduit. It's ellipsoid
sunshine,
shape, 2 to 3 feet wide, 6 feet in the other dimension.
And here we go, down the vent. And you can see it's still a slot.
So it's in air, it's not in water yet.
So far, it's really quite a narrow slot,
It's going
just a
down
few inches wide.
till it reaches the
You also
boiling
see
water.
occasionally drops of water falling down. You'll see those as we go. See some fractures and cracks in the sidewalls. Although the sidewalls actually look very smooth, and that's because they're covered with the center material. About whether we're going to land on that and not get off of it. And we
I'm afraid it doesn't get caught and couldn't get back out.
and kind of
would be
bang
a
up and down a little and a
catastrophe
hop
for
over
the
the
park.
edge, which is not coming from our housing. Now we're landing on this flat little platform of rock and banging up and down, and see if we're lucky and can get over the edge of this ledge somehow.
We've been over a ledge.
We've known about this ledge from our measurements before and always wondered what it might be. In fact, we thought it was probably a narrow place in the slot, but in the picture as we were coming down a moment again, and now it looks as though we've gone over the edge. So we've been lucky and got past this ledge. And we're down into a much bigger open area now. You can't really even see the far sidewall quite yet.
Still in the air.
We see something very striking.
Hot air.
Was a big mystery to us as we were watching this in real time. It's clearly just wildly boiling water, which is boiling up and splashing all over the camera. We had not really intended this camera to be submerged in the water, and so we were quite concerned about this, and we actually stopped at this point and came back up a little bit to think about what we were seeing and watch it a little more. And we did realize at that point that what we were seeing.
And they stopped. So that's a first downhole video and only downhole video gives the dimensions of the orifice of the conduit. And he shows it, and I will show you here. oops, I want to go forward. Well, I've had some interesting experiences at Black Opal Pool, Lower Geyser Basin. This is Black Opal Pool right here. And we had stopped with a field trip in 2009, and I had just lectured how rare earthquakes were, volcanic eruptions, and my colleague Hank Hessler, the park geologist, was making the same comments. Very rare do we ever see any kind of these events. Right behind our back, it blew up, literally 20 feet from us. So that's an eruption of Opal Pool, and you can see it blew out rock. These are rocks in ejecta that were about 20 feet high. You can see the rocks coming out, and the hot water surge comes down, and there's evidence, of course, for multiple eruptions of this. This was 2009, and since then, it's gone off many times. But this is my experience. So I heard this thing blow up, and I thought it was a truck behind my back. Well, I had 30 people behind me looking at the eruption. I turned around and saw, whoa, I better, shall I save my life or theirs? Fortunately, I tried to get my camera out, no time, but there were 30 cameras shooting me. But the eruption only lasted a few seconds, and wind was blowing from left to right. No one got hurt. That is a hydrothermal explosion. That's tiny in relative size to many of Yellowstone's hydrothermal features. Now, Yellowstone is not hot. Everybody says, oh, Yellowstone's this hot place. No, the average temperature of Yellowstone's a high mountainous plateau. And over here, I plotted the heat flux of the western US. Heat flux means we measure the amount of heat that comes out, say, a square meter. And the average heat flux is 2 watts per square meter, plus another 500 of conduction. So if you take a boiling pot of your coffee pot, it boils. If you measure the amount of heat that's coming out by measuring the temperature at the bottom of the pot and the top of the pot, you can get an idea of how much heat flow there is. That's third. On the other hand, and I've contoured them here in milliwatts per square meter, and red means really high down to low in blue. You can see the stable North America is relatively low thermal release. Snake-River Plain is higher, higher, higher. When you get to Yellowstone, and bang. And here are the numbers for Yellowstone. Yellowstone Plateau, including North Geyser Basin, produces 40 watts per square meter. How many of you have a 40-watt light bulb in your house? So if I could capture that heat, I could light a light bulb. And the numbers of the heat flux, as you can, it's hard to see. 58,000, 41, 2,000, 44,000. That's watts per meter per square meter. There's an enormous amount of heat coming out of Yellowstone because it's emanating conductively and convectively. Now, earthquakes occur in Yellowstone, and I happened to be around in '59 when the Hebgen Lake earthquake ruptured, and it was in August. That earthquake produced a fault scarp that was 22 feet high. It's actually 3 students tall. That's the offset of the Hebgen Lake fault. The mountain block is behind us, and the valley block toward West Yellowstone is in front of us. That's 7.5 magnitude. The displacement's 22 feet. And the roads were closed because of all the rocks that came down, and these roads were closed for over a week. And if you know the Craigheads, Derek and Charlie were just kids in those days. They're now adults, of course. The Craigheads were there, and the pictures were taken. So roads closed, and it was still almost 20 miles from the epicenter over by West Yellowstone. Well, who first recognized earthquakes? Ferdinand Hayden, this first geologist that came in 1872, camped at Mary Bay. There's Mary Bay. There's the Lake Butte lookouts up there. So it's just east of Fishing Bridge, about 5 miles. And he says in his notes, This morning, about 1 o'clock, we had quite an earthquake. The first shock lasted 20 seconds, followed by 5 or shorter ones, 6 shorter ones. Duncan, who was on horse guard, says the trees were shaken and the horses were lying on the ground and got to their feet. We had 3 shocks during the morning. They went on to record earthquakes continuously all the time they were in the lake area. And they were right, because Yellowstone Lake is an active earthquake zone. Now, how do we know this? We operate at the University of Utah a network of 30 seismographs. These are these triangles. I won't go into the details. And GPS. So we have GPS units that transmit continuously the ground motion. Seismic picks up the earthquakes. I won't get into the detail, but we spent about $10 million in developing this whole monitoring system. And at the University of Utah, we have a big computer facility where all the data come in real time. And all the data I'm showing you in real time, you can get from our website in real time, as fast as I can see it. Here's a station at Canyon. That's a GPS antenna, solar panel. Earthquakes on a series of seismograms from a Yellowstone lake swarm. These are each 1 day. Here's one Norris, Upper Falls, Promontory. And these are 24-hour records, which all these red things are little tiny earthquakes being recorded, if you wish, on paper. This is being recorded electronically. So these earthquake swarms start going off, and we can get thousands of earthquakes per hour of magnitude down to -1 and 2. Well, earthquakes are a big thing, and I recognize this belt of continuous seismicity all the way from right around St. George, Nevada, up through the Wasatch Front, and then out into western Wyoming, creating this parabolic-shaped zone of earthquakes all the way up to the Canadian border. It's called the Intermountain Seismic Belt. I named that back in 1974. If you start looking carefully in the area, here's the Teton region. Earthquakes come up in a diffuse pattern. Then there's a gap of earthquakes along the Teton Fault, but then you get these north-south zones of earthquakes in southern Yellowstone, and then here's the zone of earthquakes that are actually aftershocks of the Hebgen Lake earthquake that occurred right here. So this is the most seismically active area in the western U.S., excluding the San Andreas. And the earthquake zones, they get thousands of earthquakes per year, magnitude -1 or 2 up to 4 or 5. And I point out there's the Hebgen Lake epicenter. 1975, we had a magnitude 6.1. So you see this zone of east-west seismicity, and you see these north-south zones, which I'll show you in just a moment what they mean. Earthquakes in Yellowstone tend to be swarms. They don't have a shock and then an aftershock. They just, like a buzzing bee, just suddenly you get hundreds or thousands of earthquakes that can last minutes, days, or months. And in blue are the swarm earthquakes I just plotted to 2013. Half of Yellowstone's energy are in swarms. Now that's not the same for the San Andreas. Earthquake swarms are common in volcanic zones like Japan, the Ring of Fire, Hawaii, etc. They're dominated volcanic systems by this swarm activity. Now in 1956, I was employed, as I said, as a GS0, which meant I got to go all over Yellowstone and get paid in the backcountry. I went down to Peel Island at the south end of the South Arm. So this is a boat dock, and the fish egg station was here to my left, about 10 feet. I came back in '73, and the whole boat dock was underwater. And my companion, Dr. Kenneth Deem, the director of the University of Wyoming Research Center, was taking stomach samples with a sage rod. Excuse me. Don't you guys fly fish? It's the best fly fishing in the world. And you can see, we could see the water over here was killing the trees because of the tilt. Now I'm going to show you what we started measuring how the ground was moving. And we discovered in 1979 that the whole caldera was rising along this zone, up to a meter. So we knew something was dramatic. I know I've got to hurry. 1 meter of uplift. Start putting in GPS. This is a backcountry station. And the GPS for all of Yellowstone looks like this. Outside of the caldera, these are daily points from 2000 to, well, 2017. Outside of the caldera, nothing's happening. Inside of the caldera is precipitous uplift. We didn't know what was happening. It was going up, and then we had this earthquake in 2014, and the uplift went from downward motion to a rapid uplift. 17 centimeters per year. That's 5 inches a year. That is exceedingly fast. Well, what happens is you have magma coming up, and I'll show you, inflating a body called a seal, like a mattress full of partial melt. It lifts the caldera up. Outside of the caldera, we trigger earthquakes. So the earthquakes we were measuring were triggered by this magma system. Well, how do hydrothermal systems work? You have magma heats water. The water breaks the seals at the surface and it comes up. This increased heat flow, hot water breaks, and you have hydrothermal features. Here's what happened in 2002. It was a big earthquake in Alaska, and it sent seismic waves from Denali all the way down to the western US, and when they hit Yellowstone, bang! Those waves cause Yellowstone Park. These are all the earthquakes in red that were triggered by the Denali earthquake 2,000 miles away. So the contagion between Yellowstone and distant earthquakes is well proven. And the changes in geyser activity was done by the same event. Riverside was slowed down, Daisy Geyser were slowed down in their eruptive intervals. Now, I showed you about these earthquakes that come in from the west, Hebgen Lake aftershocks, and then all of these vertical lines here in yellow are fault zones that are covered by volcanics, but along which magma has come up also. Here's what we're doing now. This is the heart of my talk. The community invented what we call nodal seismographs. And here I'm holding one. They're totally autonomous. They're self-contained. They have their own electronics, their own storage. We take these out and we stick them in the ground. And they run for 2 to 3 months, totally unattended. We have 200 of these now. And we do it after the park closes in November, so it can be kind of chilly. Here we are installing one with a hole. We're allowed to get in close to the orifice of Old Faithful that time. There's the orifice, there's one of these nodals. You know, it's kind of cold that time of the year, but we're prepared for it. And we essentially monitor and measure ground motion. So we put in all of these seismographs starting in 2015. And I'm going to focus on Old Faithful, that's the star, and Geyser Hill to the north. And here's what we found out, that the ground starts shaking right before eruption. So the eruptions of Old Faithful are these arrows. These are individual stations. You can't even see the eruptions. They're insignificant. But they have this harmonic tremor. The ground is shaking for 20 to 30 minutes, and then it goes off. So we discovered these things, and we're now following them closely. In 2018, we did the same study at Old Steamboat Geyser, same instruments, right behind the geyser. And we're allowed to do this after the tourists have gone. And we get the same kind of a pattern. Down here, we're just showing you a day of data. Each instrument is on, and this is the parking lot down here. So all these patterns of points are people and cars. Now watch up here. Gibbon Hill, every once in a while, just pops off by itself. We have no idea why. Well, Geyser Hill, bubbles, here's Doublet Pool.
and doublet pool rises and subsides 2 to 3 inches, and when it rises, it emits a lot of CO2, and when it emits the CO2 during the bubbling phase, we record these signals. So this is now becoming a common signature of these systems. There's doublet pool. And we see the reservoir load and then unload. And here's what we discovered. Taking all these data, doing tomography, we found a body, which is the Upper Geyser Basin Hydrothermal Reservoir. It goes all the way from Old Faithful, clear over past the inn, and you can see it's shallow as only 5 to 10 feet, and as deep as only maybe 100 feet, 120 feet. This is the reservoir that fuels Old Faithful. Old Faithful is not a big deal in terms of geology. There's dozens of Old Faithful remains, but here's where it covers. So here's Old Faithful. That body goes clear out to the inns, to the Old Faithful Inn parking lot, over to the lodge. This is that body itself. And if you look around these circular patterns here, these are old Old Faithfuls, prehistoric. So it's an active system. Okay, here we go. This is a movie watching with time how the fluids are going to rise. Here they come. We can map them as they rise from only 60 meters to the surface, and then bang, they hit the surface. And over here, we're plotting the pre-eruption depth, and then there's a cutoff, and you go down to the top of the system. It's 80 meters, then it rises again. Every how many minutes is Old Faithful going off? 95? Well, here's what we think it is. Here's the hydrothermal reservoir. It fills. It finally goes up into that reservoir with hot steam and water. And the bottom that can be measured only if you can see 10 to 20 meters. And then it goes off. So it's like clockwork. The clockwork is because how long does it take to fill this chamber and this chamber? 95 minutes. Now it changes with time, of course, depending upon the reservoir source. Guess what? We had a bison come over and he had a football match. Now, we actually recorded this bison. There he is. This is a seismograph from this instrument. We can actually measure him walking over, then he stops and looks at the instrument, and then he kicks it and knocks it away. I have his footprints. If you guys have a record, I'll go get him and give him a ticket. So let me just finish off saying Yellowstone is really a geologic park. Steamboat is the world's largest geyser, and I was lucky enough to be able to take those pictures. Here's Norris Geyser Basin. I'm showing it to you because now it's erupting in the last 2 years so frequently. It's everybody is watching it. There's an eruption up close of the Norris Geyser Basin of Steamboat Geyser. And here's a list of all the eruptions. There's 58 of them in 16 months. So the eruption time has decreased from 2 weeks over here now to 5 to 7 days. And the geyser gazers are out watching them, and we can predict pretty close when it's going to happen with our data. This is some data that I just got from Julie Jones on the eruptions per year. And this is some Gosha. I didn't have time to write a title on it, but you can see 2018. This is the active phase right now, days beginning from the start time. This is a very active period. Then there was a 1980s active phase here, and the eruptions per month. Here's the eruption, very high now in this 2019 window. Why is it happening? I'll explain it, because people said, Dr. Smith, why does it do this? We published this paper. Here's the upper 1,000 feet. Water comes in to a hydrothermal system. There's the water table. You drill for your water. What happens, there's a pressure versus temperature plot. Here's the pressure of the water and the temperature. So the water table's high. Then if you drop the water table, which the water table goes down every summer, because you withdraw fluids from it, the Earth does,
what do? You go from P1 to P2, and when the pressure increases, the fluids get out easier, and you have a lot more eruptions. So we can actually time these from this kind of a model. We know there's an active magma reservoir beneath Yellowstone that extends from the south of Old Caldera, but what people don't realize, it goes clear up to the northeast side of Yellowstone, way beyond the Mirror Plateau, up to the Lamar Valley. This is the seismically imaged magma zone in a new image in yellow from our new Caldera mapping, gravity mapping. This is a fun one. So here's a seismograph at Old Faithful. Look at all the people. They're all running around, thousands of them, but we have seismographs all around there. So here's one record from this particular station, plotted versus time. This was in 2016. This period of time, these spikes are eruptions of Old Faithful. There's the eruption, 1, 2, 3, put them in red. At nighttime, no one's out there, right? In the morning, 7 o'clock, there they come. Those are people and cars and people and cars. Now, here's the key. There's an eruption, number E10. People are, and they suddenly leave. There's an eruption E11, and they suddenly leave, E12. Do you know what that correlates with? The number of flushes in the toilets at Old Faithful. It does. I've got a figure if you want to see it. At least they held their water. So when magma comes into the system, it spreads laterally. This is a mapping one of these swarms at Yellowstone Lake. Magma comes in, but it not only goes up, sometimes it just goes laterally, time from left to right. And when it does so, it creates earthquakes. These are all the earthquakes paper we published a couple of years ago. And we've actually modeled how these swarms migrate. Well, I just want to finish off here. That's the Old Faithful hydrothermal source. Old Faithful itself is minor. This body is this body right here. And so we know why the ground is so hot beneath the geysers, the hot springs in the roads, and why in the winter there's no snow in these parking lots over here, because the ground is so warm. So I go back and I finish off. We have a mantle plume fuels a lower magma chamber, and an upper magma chamber gets fueled by heat. This is the one that produces the heat that goes into these resurgent domes and created the Yellowstone caldera. And notice that heat, that body goes to the northeast beyond the caldera by at least 15 to 20 miles. I tried to depict that. What's the hazard? I'm going to show you a pie chart, just the probability of something happening like a super eruption, 0.00014%. Don't worry about it. But I put in the risk factor, it's still 5.6% of that pie chart. But these rhyolite flows, that's what created Yellowstone. 2% of the total. They're small, they're insignificant. Hydrothermal eruptions are big because they're very active, and the problem is they're very small in aerial extent. So there's the blue piece of pie chart. What's the biggest threat in Yellowstone? Earthquakes. 95% of the risk and hazard in Yellowstone are large earthquakes. They killed people. Hebgen Lake earthquake killed 28 people in 1959. The potential for these kind of large earthquakes is very high. It's the highest in the whole interior West, except San Andreas. So let me finish off by saying I plotted here numbers of earthquakes on the left, and these are these graphs right here, number per quartile for 3 months. And swarms are in blue all the way up 2016. Then I plotted the uplift from GPS. That's the uplift rate over here. And so the caldera goes up. Then there's a huge earthquake swarm in 1986. And suddenly the caldera went down. And it went up and down, then it really went up 2005, and we had the big swarm right here. Outside the caldera, when the caldera went down, outside at Norris it went up. Caldera goes down, Norris goes up, sympathetically, because we're taking fluid out of one body and putting it into another. But the important point is this. If we didn't have these earthquakes here and here, they're the relief valve that releases the magma outside of the magma reservoir. If we didn't have those, guess what we're going to have? An eruption. So we're tracking this very closely to see what happens when we have big earthquake swarms and how the caldera is deforming. So I call it my Yellowstone relief valve system. Oh, I get to show you what I did in my life. Just a minute, so don't run yet. I'm changing. This is for Bob Richard. I was a pilot in the U.S. Air Force class in 1962. G. I know it doesn't look like me, but it was. 18 months later, I was on the Antarctic continent as the United States Exchange officer with Secretary of State Dean Rusk as my boss. Guess what I was driving? A dog team. Have you ever driven a dog team? They're serious business. Oh, we had snowmobiles and we had little airplanes, but that's me driving a dog team after I learned how to fly jet airplanes. And we were down in the Bellingham, Palmer Peninsula. This is our ship. This little guy right here, we got frozen in. I mean, frozen solid. We couldn't get out. We stayed and stayed 3 days, 4 days. I finally got on the radio telephone, called Washington, D.C., and I said, this is Lieutenant Smith, and we're stuck. And the captain of the ship said, we have enough food to last a year. And I said, I'm not staying here a year. So the Antarctic Service said, Lieutenant Smith, wait a couple of days. Something will happen. And the something that happened was the biggest icebreaker in the world. Came from McMurdo Sound, clear around Antarctica, came around us, pulled in front of us, and we followed her out. That's the USS Glacier. There was never a communication between ships because of protocol. Don't want to embarrass the Brits. Here's the British toy, the big icebreaker. Now, they just released this information a few years ago, so it's now public. But I didn't stay there. We were doing geophysical surveys. This is a gravity observation. You can see these are big basaltic dikes. We use dog teams. Taking a dog team, we went clear out 25 miles, and we went through a crevasse. There were 3 of us. There was myself, the base leader, and the base doctor. Okay, here's the base leader. He didn't go down, but see these 2 ropes? One's me, and one is the base doctor. He went down 30 feet and had a compound fracture. I went down about 10 feet, and it turns out I had a fracture. But here's the base doctor. He's looking up because he had a camera in his pocket. So that's looking up. We're looking down at him. What the hell are we going to do? Well, he got me out, and then he got the base doctor out. Here he is, and shot him full of morphine, then shot me full of morphine, and it was about 15 hours of sledging to get back to our base. He set his own compound fracture, and he set my compound fracture. The nearest airplane was 3,000 miles away. This is Antarctica, folks. We were right by Shackleton's grave. How many here ever heard of Sir Ernest Shackleton, greatest Antarctic explorer? Went down 4 times. The last time he was down, 1915, he died at South Georgia, and I've been to his grave site a few times, and it's pretty heart-wrenching when you go there and see this gentleman is buried there. I got the medal from the United States on the left and the British gold emblem from the Queen's contribution to the British Antarctic Survey for that service. But I'm a skier. I've lived in Switzerland. I've been a professor at the Swiss Federal Institute of Technology. And I just want to show you guys what a young skier. There's me and one of my colleagues. We love to ski this backcountry. We call it randonnée skiing. We get to the top of the peak. What do we break out? White wine. Then we have to ski down over these cliffs. There's another one, Pete's Juve. Going up to this hut, we skied all of this. I've skied the entire Haute route. Anybody heard of that? The high route from France to Liechtenstein. This is, again, Pete's Midel, in the middle of we skied this whole ridge. And we skied this edge of the Berkshire and got over to the peak. Now, there are a bunch of truck drivers Swiss truck drivers in this hut. Have you heard of truck drivers skiing? We got to the top, and they all followed us. Here's all these drunken Swiss truck drivers. And here we are skiing Mont Blanc, the highest peak in Europe, on the west side. That's Mont Blanc. We actually skied to the left. We got down in here. It's called the Guy de Queen. The problem is there's all kinds of avalanches. They were coming behind us and in front of us, but we made it out. Okay, Californians, here's what we just had to finish off. July 9th started out with this big swarm of earthquakes at Ridgecrest, California. And we had a magnitude 6.4, and a day later, July 9th, 7.1. And so here's the earthquake sequence. It's, of course, online in real time. This earthquake sequence, that's a big earthquake, 7.1. Hebgen Lake was only a 7.3. San Andreas can put out 8s. And that's what the earthquakes look like in the first 2 days. So the earthquakes, the earthquake started down here and they propagated up past Searles Lake. Bob Richard, this is the Navy China Lake base. So it goes, they're not telling us how much damage they have. This is still QT with the military. But a lot of earthquakes and a lot of damage. They think up to $100 million in damage. Now, Yellowstone triggered earthquakes, not likely. It's 900 miles from that earthquake to Yellowstone. Now, I said it's not likely because I already showed you from the maps that Yellowstone get triggered by Alaskan earthquakes. Why can't we be triggered by nearby regional earthquakes? And just let me finish off by saying this is the literal end of us if we have a super eruption. And there's my website. You can go after, I can tell you, don't you have to write it down. But I want you to visit Yellowstone before it visits you. So my advice, everybody go visit Yellowstone quick. And if I drive down the road fast, follow me. Because you want to visit Yellowstone before it gets you. Thank you. That's the end of my talk.